Whoa. Thank you.
Okay, there you
Thank
go.
you, Selen.
Thank
Happy to be here. I don't know. I will do my best to present this topic because the previous two sessions here were amazing from a lot of smart guys. And well, I will try to keep up. This talk is actually very interesting to me because this was a problem that I have been facing for in many different companies that I have been working in the last few years. And thanks to graphical models, I find a solution. So hopefully after this talk, some of you, if any of you is facing the same problem, will have a new gadget in your toolkit in order to solve it. The agenda is very simple. I want to introduce you about marketing measurement. All this example in the talk is around a marketing problem. I will guide you through the ecosystem. We will talk about what's the actual problem that we are trying to solve, what are the tools out there that make solutions possible, and then hopefully we can have some Q&A by the end and some conclusions. So, quick slide to introduce myself. I'm Carlos Trujillo. I'm working for Wise, or formerly TransferWise, if you ever use the application to send money abroad or pay with our card. And at the same time, I'm working with PyMC Labs, developing open source products. And by the way, I'd really like to make questions because otherwise this feels like a monologue. How many of you have been ever using PyMC for, raise your hand. Oh, amazing. We have a lot of people here that use PyMC. So if you use PyMC and you ever left a comment in any of the PyMC ecosystem libraries, probably I reply to some of them, probably not. Maybe I work on some of them, or probably not, I don't know. But I'm part of that community as principal data scientist. So the question that I will introduce today is, as I mentioned, in marketing, and it's very simple. When you work in a marketing team, your CFO asks you this very simple question: where should I put my money? Marketing in many companies is observed as an investment. As any other investment, we want to see what's the profitability of it. Like, should I put my money in this marketing campaign and activities, or should I just put it into the stock market or in a, I don't know, fund or whatever? And companies dedicate, and this happens in that way because companies dedicate a huge amount of money in marketing activities every year. This is a huge industry. We have large teams in every company just trying to figure it out how to make people consume more of your product or service, which ends up being, again, interesting because in order to reply this question or to answer it, we need to measure it first. And we have been changing the way of measuring marketing in the last 15 years because as anything, we have a lot of cycles around measurement. 5 years ago or 7 years ago, we were doing a lot of digital marketing, and by consequence, we were using, let's say, things like Google Analytics. But again, how many of you know about Google Analytics? Raise your hand. A lot of you. Great. So, as you can imagine, not everything is digital. If you do, I don't know, ads in the subway, or if you do ads in the radio, you cannot use Google Analytics to measure them. And that's why we came to marketing mix models, which is precisely the problem. And what we are trying to do with marketing mix models is to create a function that can understand our ecosystem and by consequence decompose it so we can see which are the drivers from our media, like again, digital ads, non-digital ads, that are driving the most of our performance. And again, you could see this and think in a very simple regression, but the truth is that this regression has some peculiarities. We encode causal assumptions into it, in the structure of this equation. When, for example, we say that marketing should have a diminishing returns law, we create a function that, in this case, I just put it as an f, that gets an input, which is our media spend in different platforms, and in the function will translate this diminishing returns effect. At the same time, you can also encode other functions like carryover effects, which basically means how much of this marketing impact not only translates today, but translates into the future, how much is delayed or lagged. And all of this will, by the end, tells you how much you should invest. Hopefully, that's the goal. But as I mentioned here, already with this equation, we are doing a lot of assumptions. We are imposing a structure over a system. And in marketing, the most that we want to understand in order to reply the question properly is understand systems. And in order to do that, we use DAX or Causal DAX, direct acyclic graph, where we dictate what are the relationships that we are trying to explain. We have many things happening outside of our world, in our environment. We have macroeconomics, we have, like, I don't know, discounts, we have the weather, we have the marketing activity, of course. And every one of those, some of them are observed. Like, again, we can see the weather, we can check some macroeconomics values. But for example, we cannot know what is the amount of spend from our competitors, or what is the interest in a specific product during time. Those type of things, we don't know them. But even though they affect our system, and by consequence, we hopefully want to control for them if we want to explain our system in the best way possible to, again, answer the question of where should my money go. And the most problematic thing about this is that these systems are complex, because many activities will dictate many different outcome variables. So you spend in marketing, again, but you could get new users, you could get recurrent users that probably churn and then they came back, or you could get, I don't know, churn users because you put so much marketing that they just decide to go out of the platform. Like, many things can happen. And your job when you face these problems is transform all of these, as I mentioned, all of these different DAX into different models. And to do so, we will make every of these models, every of these different variables, a structural causal equation. So again, you have a big ecosystem, you can draw the ecosystem with a DAC, and you will then, based on the DAC, you will build several structural causal equations, which hopefully will explain different variables. One equation probably is explaining new users, other is explaining retention, and so on and so on. You can have another more for LTV, whatever. You will have, depending on how big your ecosystem is, a series of models that are trying to explain it. And this also comes, and why you have a series of models, and also it's because it's practical than try to build a huge model that explains your whole ecosystem. Like, that's some path that you could try to go through. But at the same time, that's probably the most difficult thing to do. So what do you think that is a problem here? Like, we have, some problem that we want to solve. We are doing a lot of models, and then what happens when we have many variables of interest that we are explaining with different models? That's basically the introduction to the problem. And the problem is, when you have different models, those models sometimes contradict each other. So we are trying to find out where to put our money, but then model A says, well, you should put your money in Facebook to get a lot of new users. And then model B says, put your money on Google, because we need more re-engage. We need to re-engage more churn users. And then if you go to your CFO and ask, like, okay, we have these two, like, what should we prefer? Probably your CFO will just say, I want everything. And you're like, okay, we cannot have everything, but I want it anyways. Optimize for it. And again, this is a problem, because this will imply in many cases that either you need to find a way to combine the models, either you need to find a way to combine the output metrics in whatever type of combination. And again, those paths are problematic itself. So that's when I find, until at least, where I find out about graphical models. And because all of this is happening, by the way, as I mentioned, in the PyMC ecosystem, and you, to a certain degree, are already doing graphical models since the beginning. Again, we were translating these causal DAX and these directions of how variables are related into equations. So we already, until a certain degree, already a graph of what do we expect. We can then use those same properties that are already built into the model to combine them. How does that work? So let me give you a small introduction about graphical models. So graphical models are a very nice way to represent mathematics. So, as I mentioned at the beginning, you can think of, well, if you have a causal DAG that is saying which variables are connected, you are also defining what are the variables that should exist in your equation. You are also defining what are the direction of the relationships that should go into your equation and how your equation should respect those laws. And that makes, very intuitive to understand what do you need to condition on in order to capture a specific effect. So if you want to capture the effect of Facebook, and Facebook is dependent on n number of variables, then you know that if you want to find, I don't know, the minimal adjustment set for it, you can use A or B in order to capture it. You don't need to actually use the full system. That's a bit of causal theory there. And this also, again, becomes handy because you can, as I mentioned it, can see the variables that exist, the variables that depend on your ecosystem, but also allows you to decompose the ecosystem in small pieces. So you can take a graph, as I mentioned, you mutilate it in a way, and you create different equations that they are all coming from the same mother big system, but each of them represents a small part of it. And again, this becomes handy with libraries like PyTensor or TensorFlow, where these graphs at the same time are a form of a symbolic representation. And this just means that you can create this graph and all the math that happen under the hood without the need to actually generate data. So you can have, let's say, the graph and the data are separate objects. You will have your data from one side, you will have your graph from the other, and if you need to do any operation, like merge a model, you don't need to retrain. And that's very handy because, again, in a regular type of solution, if you're doing, I don't know, scikit-learn or any of any of the ML type of libraries, you will just need to rebuild the model because you don't have a graph and data separate, like everything is just combined into a single object. So you need to find a better way to represent your big structure, probably retrain your model, you will get new values out of it. Those values will probably change, and then you will need to define, try to defend to your stakeholders why this new model that is now bigger and complex, it's better. But if you have a graphical model, again, if you have a PyMC model, where, again, the data and the graph are separated, you can actually play with that graph, create a new model, and you don't need to retrain the model at all. You can just use the data from the existing pre-trainings, where you learn the parameters, in this case, learn the posterior, and then infuse that information into the graph and do all the operations that you need. And again, this will be very similar to take two SQL tables and do a join. And you can do that join because the graph, because they're explaining the same system, share certain characteristics. So probably here, many of you are asking, what do you mean about merging models as SQL? That's crazy. I don't follow. I will try to put it into a picture, but imagine this. You have different nodes into your graph. One of those nodes is shared, and then you combine those nodes in order to get a set of equations that run in parallel. So you, again, have two different graphs that depend on the same variable. You can combine them. You will have basically like a tree where you have two independent processes depending on the same variable, and all of that can run in parallel. And that's basically the same to run a system of parallel equations. And this is, right now, out of the box available in tools like PyMC Marketing. So if tomorrow I need to solve the question where I should allocate, I could go and say, well, I know that I have a set of variables that are depending, that generate different effects. I can combine them, I can create a new model, and then I can use that model for optimization. And that's basically what happened under the hood. So you will have a set of PyMC models. Those PyMC models can be merged given a variable, in this case is channel data. So this is the common node in both graphs. Once the graphs are built, you can now print the new graph from PyMC, and you will see that you have different independent operations that are happening under the hood. By the way, Um, I want to make a stop here because how many of you have ever used this function like pm.model to graphics? A lot of you. Nice. So again, this function is not just there just because. This function is trying to explain the computational graph behind our model. And that's, I want to stop here because this shows you that when you're doing any PyMC model or when you're doing, even if you're actually, by the way, this happens even if you're not doing PyMC. Because all of these graphs, what are encoding are the assumptions that we have underlying our process. So in a regular Bayesian framework, you start asking yourself how the variables are connected. That's the initial graph nodes where you just have names and arrows. That's the causal duct, how they are connected. You formalize those connections into a structural equation, so you give them a form. In this case, we build the functions where we're defining something like, okay, we will have saturation and we will have add stock, and they need to be additive effects, or they could be multiplicative, and so on and so on. And then that math needs to formalize into a computational process about how those calculations needs to happen. And that's why PyMC puts this there, because now you will not have this, beta coefficient. That beta coefficient will become a random variable in this case, which is a distribution, and that distribution will be calculated among other set of variables. So all of these assumptions happen all the time. You have assumptions about underlying distributions, about underlying connections, about underlying structure, and in a set of tools like PyMC in an ecosystem like this, those are transparent. You will see at every step that you are doing what you are doing and why you are doing it. Different to sometimes when you use other libraries where all of these things are just encoded and you think like you're just doing, MMN.fit, and that actually is taking a lot of steps out of you without you noticing. So graphical models are just, I will say, really a really interesting tool to have transparency around all the steps that you are taking in a model. And with all of these parts together, then optimization becomes really easy, because now every of your variables of interest and every of your exogenous variables are in a place where you can play with them. So let's say if we have this problem, how I should or where should I put my next dollar, a very, very nice ways to solve it could be, let's create a composite metric. Now we have this new model that has all the variables that we need. Let's create a composite metric that sort of reflects the trade-off between new users and re-engaged users, and put it into the solver, try to maximize it or minimize it or whatever you want to do. That's one way to do it. At the same time, that have their flaws. Probably I will ask like, okay, what this new composite metric means. It's new users, it's re-engaged, it's like the sum of something. Like, why are we doing it this way? Like, that's putting extra assumptions in the process. Another way could be, you can have some Pareto law where you try to find, that limit between both. But how we prefer to define it is, well, we will always have a main variable of interest. Like, again, your CFO probably have more interest in getting new users and make the grow base grow than retain the existing ones. So if that's the case, but he don't want to fully forget the users that are already in the platform, you can set that metric as a secondary constraint into your optimization process. So you will say, okay, I want to maximize the number of new users, but I don't want the re-engaged users to be less than 200. Tell me what is the best budget that I can put in each of my strategies and each of my different placements that can satisfy that constraint and give me a certain output. And again, do something like this if you are writing SciPy, will require like different steps. In PyMC, is as simple just as generate a function where you define what you want to maximize. In this case, is new users, and you define the constraint, where all what we are saying is the constraint needs to be greater than certain threshold. So we put the threshold, we define the function, we pass it to the optimizer, and this under the hood handles all the machinery so you can get an output. And with this, we came to solve the answer. So if tomorrow my CFO comes to me, I can go and show, okay, these are the trade-offs. We have, on one side, we have the model where we only care about new users, that will be the orange one. And you can see that if we just follow that model, we don't need to spend any dollar in X1, or we need to spend a few less in X2, but where we actually need to put the majority of our money is X3 and X4. If we see the other model, the re-engage one, it's the opposite. So you have X1 and X2 where you need to put all your money, no money on the last two, which are X3 and X4. But if you have the merge model, which is now, again, putting all of this together and is creating a new framework, you have some more balanced set of body distributions. So here we can see that we are not turning off completely X1. We are leaving some money there. And we are not going crazy in other ones like X3 and X4 as well. So we are trying to balance in the two objectives that we initially had. And again, this is possible because we have been putting all our system in the same place, and we have been framed the optimization properly. So I will go to a few conclusions, and they are very biased. I really like graphical models. So it's very obvious that the first is like graphical models are great, because they are. I think like they allow you to make a lot of different operations. They allow you to play with your models without the need to retrain them. And this becomes also like handy, because that also means that, let's say that tomorrow you have a change on your assumptions, you want to make a different model of the world, you could actually do it, and if the parameters didn't change, you can use your storage data and impute it into those new graphs and see what comes out, and see if what comes out makes sense. So this is, again, thanks to their symbolic properties. So they are very transparent. You can see everything that is happening under the hood. This is not just a black box model that you cannot understand. You can open the graph of your models, see what is happening under the hood, and solve like any doubts, and actually catch any bug if that's something that was introduced without you noticing. Here you will explicitly see it. And also doing this, graphical, like once you're in the world of graphical models, then complex systems becomes very trivial, because you are explaining them from the beginning. You are able to split them as if they were Legos. So you can explain smaller parts, then came back and assemble everything together into a big chunk. And all of that is just, out of the box if you are working with this type of tools. So I hope that any of this is interesting to you guys. And I'm really grateful for this time. Thanks.
Thank you, Carlos. Very interesting. I have a bunch of questions for you from the audience and myself, obviously. The first one goes like this. What are some practical solutions to data drift? For example, shifting consumer preferences from a data science perspective.
If we are talking around the model itself, I think like one common step that we are doing right now is add these time varying components into the models. So if you know that you have these drifts in preference from channel to channel, you can go and create these latent variables inside of your models that try to capture those drift. And then again, you will need to define it hopefully in your graph, and then impose the structure of how these changes should happen and which variables and which parameters they should affect. So once the model recovers some parameters, you can see those, again, variations as well inside of your model.
Is there also a way to kind of connect this to the actual marketing work that you do? I mean, when do we get marketing on autopilot?
When do we get marketing on autopilot? That's a, I don't know, that's a good question. I think like right now we are getting...
Just a little challenge for you.
Yes. I think that right now we are getting closer and closer. For example, we already see that there is opportunity to make these media mix models using AI or using agents. So you can create harness that know how to build this model and how to question them. And what we have been seeing is that once you plug things like Claude 4.7 or something like that, they actually deliver quite well. So I feel like we're getting close to automate this marketing part. If you want to know more about that, you can just go to Decision Lab repository. That's a specific harness that we developed to do agentic MMM. So you can see how we develop it, what are the decisions that we put under the hood, and basically this is just, again, an agentic framework that allows you to build media mix models without human intervention. Hopefully you can just prompt it like, hey, I want a MMM, and then Decision Lab will do everything for you.
But currently it's more like a decision support.
Yeah. Right now it's just more for support, so yeah.
Yeah. Okay, the next question is about your presentation, actually. Very nice animations. How did you make them?
Claude code.
Claude code.
Yes.
Okay. Very simple answer.
Yeah.
Very good. Also very probably very usable for all of them.
Yeah. It's to be honest, you just ask Claude code like, give me this in HTML and render, and
very good. Yeah.
He just do it for you.
Okay. About the correlation between the number of models to the number of contradictions, doesn't this mean that one of your models are wrong? Is there a silver lining there?
That's very. I don't think so. I think like in any complex ecosystem you will always have variables that goes against each other, just because the number of, again, variables go big. That doesn't mean that your model is wrong. I actually think like will be interesting that a same activity is always driving. If an activity drives the same effects, you cannot expect that effects just propagates over different variables. That will be my answer. I think like, of course, there is a room for question your model, and some models can be wrong. But I will say that go into the assumption that a single activity will drive the same effect across very different metrics, it's very fragile.
Okay. What if the constraints are predictions of other models or functions instead of just constants?
Yes, that's also a very nice point. And when that happens, what we try to do is, so in a structural causal equation, many of the values or many of the parameters can be inferred from a previous model. And what we want to do is propagate uncertainty from those towards the final. In our framework, in a PyMC framework, that's very easy to do. So you can always propagate uncertainty from higher models to the bottom ones, and you can use those outcomes as any type of constraint. Now, I will say that the question is, and this is open question because variate from business to business, is how do you quantify or how you impose a constraint when you have, usually what happens is like as you propagate uncertainty just explodes. So how do you create a constraint that makes sense when your uncertainty around that estimations is so big? I think that will depend. You will need to define that trade-off, but fully possible right now under the PyMC framework.
Okay. If there are a lot of variables of interest nodes, then optimization becomes difficult and computationally expensive.
Yeah.
Also, it's a NP hard problem. How do you deal with this in a PYMC tool?
Yes. So one of the nice things, sorry, this is what I'm saying, graphical models are the best. One of the nice things are graphical symbolic model type of libraries as PyTensor is that you can have and compute the graph over a specific engine, and then you can use acceleration. Once one is compute and compile, you can just run those calculations in whatever backend that you want. So a very simple example that we have is that we compute, let's say, our graph internally, but then we use GPU acceleration at the moment of calculating the optimization. So if you go to PyTensor, you can actually set the backend to JAX. You can set your backend to, if you're using Mac, you can set to MLX. And you can use any GPU type of acceleration framework that makes these optimizations quite fast. So, and I think, like, again, this is possible because you don't need to calculate everything at once together. You can just compile the graph from one side, and once that graph is compiled, which is, I would say, the most difficult operation, you can pass it through and start to generate data and calculate. And that basically usually makes your process faster. So in PyMC, how you will do it, answering the question now, you can change the backend. You can decide based on your hardware what is the best backend to you. Is C, is JAX, is MLX, is whatever. You just change it with a button in PyTensor, and you can run the optimization. And if that's not sufficient, one of the nice things that you can also do is in order to do optimization, you don't need to use a full posterior. So in a posterior, you have, like, I don't know, 3,000, 6,000 samples, sometimes even more, depending on your problem. You don't need all of that to optimize. You can actually optimize with a fraction of the posteriors. You can just randomly select parts of your posterior and then go through the optimization, and that also makes optimization really cheap. And finally, this is, I think, like, that was the part of how do you navigate when you have many variables. Yes, when you have many variables, your problems start to become non-convex, and many of the most fastest solvers are for convex optimizations. When you have non-convex optimizations and you have these, optimization spaces which have batches and are very difficult to navigate, what we tend to do is try to simplify it, because all non-convex problems sometimes have their convex version. And if you can solve the convex versions, that usually give you the 80% of the value. So that's a bit of how we try to handle it. And we are hopefully bringing more, like, evolutionary algorithms into PyTensor very soon, so you can also solve these non-convex optimizations if that's the case.
Okay. How can graphical models give the causal effect of each of the different variables?
So the graphical models will help you to understand which variables do you need to condition in order to capture a causal effect. Let's, I don't have a quick example right now, but how many of you, hands, do you know about colliders, change, or forks in causal structures? Yes, a few of you. Yes, nice. Well, using a graph, you can identify the type of structure that you have, and based on it, you will know what variable needs to be conditioned on in order to recover a causal effect under certain assumptions. You can read more about this. This is a topic by itself, but you can read about more about this if you go to Judy Apperelt, the book of Why, and you want to learn more about, like, do calculations or do operations. That's basically where you can find out how graphs or causal DAX helps you to recover causal effects.
Okay.
Yes.
I have two more questions from the audience. No, three, sorry. Why do we model dependencies as DAGs? In reality, we should reasonably observe cycles.
Yes, that's a really good point. And I think, like, right now, the main assumption is that explain cycles, it's way more difficult than explain not cyclic graphs. So we hold to the assumption that, well, we know that there exist some cycles in marketing, but explain them will take quite a chunk of effort, and we just go to the simplified version of, let's just try to explain first what reality looks like without these cycles. Once we solve that, we can probably move to the next topic. So, sorry, there is no better answer. We are just neglecting it in a way at the moment.
Okay. So this one goes, how do we differentiate between a necessary confounder and a potential collider that could introduce M-bias when conditioning your model?
Yes, so that's the whole field of causal discovery. Again, sorry for promoting. In PIMC marketing, you have a causal discovery module where you can actually test independencies between your nodes, between your variables, and try to find out what is the most probable DAG that is underlying your data. Once you do that, I think that in certain degree you will be able to solve this type of questions and be sure that you don't have any of those structures inside of your data. But that's basically a space of research where you need to just dig and like try to get up. You will get a possible DAG that then you will try to falsify. You will find evidence or not around that DAG and then move forward with a model and so on. And that's just iterations. But you have, again, the tool, PIMC marketing, causal discovery, and you can apply it to your data.
And does graphical models make this easier?
Yes, yeah. Because you get a graphical model after every run, and then you can have a abstraction of how your ecosystem should look like.
Okay, final question. How do you, in practice, pick your threshold Z?
My threshold Z?
Yeah, that's how the question is formulated.
I don't know what specifically, but yeah, somehow I define it. That's a bad answer. I really don't follow.
No. Okay.
Okay.
Let's leave it at that. Does it ever rain in Estonia?
A lot.
A lot.
Yes.
Okay. So maybe we should present you with a gift from GAIA for all the speakers. We call Gothenburg the city of wind and rain. So obviously, storm umbrella. Thank you so much for coming to Gothenburg.
Same.
Thank you.